Welcome to our lectures on NPTEL on DC microgrid and control. Today we are going to discuss application of the microgrid with the nonlinear control. We have already discussed with the with our linear control system. Today we are going to discuss with the nonlinear control. Now our as we have seen in our previous presentation that once you go for the different kind of control technique, you have a different kind of switching stability limits. But this since you are taking considerations of the linear model, you are averaging, and now this lot of information is lost. And for this reason, we require to reinvestigate the microgrid with the nonlinear control. Now, so why nonlinear control? Issue is classical or the linear control methods are commonly used for the DC to DC converter design that we are studying for many more days, but with more knowledge on the nonlinear control and the switching technique, we have enhanced the stability and other performance of this DC to DC converter with the nonlinear control, and thus this nonlinear control strategy can also be applied to our DC microgrid. Small signal model has been used to analyze for considering the small perturbation in the input and the load disturbance to analyze the stability and design controller for DC to DC converter with constant power load. This is one of the problematic entity CPLDs, in which system equation have been linearized around an equilibrium point and then analyzed by the classical eigenvalue and the frequency domain technique. We have seen that Bode plot, gain margin, phase margin, and we have come out to the solution. We have applied Raoult hysteresis, all the control system you have studied in your linear control classes, that has been applied here. But however, due to the nonlinearity of this system, this linear control methods are or can only ensure a small signal stability. So, if there is a large change, so equilibrium point itself changes, and thus you cannot apply a small signal analysis technique to analyze the stability for a large change signal, but they are not effective when the system is experiencing the large perturbation. For example, sudden high load change. For example, all of a sudden irradiations come down drastically, clouds comes and irradiation drastically falls to maybe 1000 watt to 200 watts. Or you may have to, you have all of a sudden fault has occurred, you have gone into the your grid connected mode to the islanding mode. These are the large change into the system, and one of the solution can be thought of is a sliding mode control or feedback linearization. The slide, but it itself is a big chapter, sliding mode control. For this reason, I request those who does not have a knowledge of this linear control strategy, of course, I can touch upon and basic essence that how it can be given, how it can be fit into the DC microgrid, and this sliding mode and feedback linearization, that itself with the multi-rate control, that itself is a very big chapter by itself. Anyway, the sliding mode and the feedback linearization method has been used for designing controller for the DC to DC controller for many days. We can find plenty of papers on it, and thus this concept can be attributed here also in the microgrid to address this large change, to ensure the stability of this low voltage DC or the medium voltage DC system with constant power loads. A controller that can guarantee a large signal stability in the presence of the both input and the output voltage, both input voltage and the load variation is needed. So, linearizing a nonlinear plant about an operating point ensures the stability only in the neighborhood of the equilibrium. So, if there is a large change over, so equilibrium point itself changes. So, all the studies which is applicable in the small signal analysis are null and void. And for this reason we require to go for the nonlinear control, and where feedback linearization is a nonlinear control approach, we take the feedback and linearize it, use for to compensate the constant power load effect, that is the CPLD. I told you this is one of the very nasty entity in our DC microgrid. Effect in distributed power systems and its effect in a distributed power system like this microgrids, where in a nonlinear feedback is chosen to cancel the nonlinearities introduced in the system due to the presence of this CPLD. Because if you have a constant impedance load, that is a linear kind of load, but CPLD essentially is a nonlinear load and it has got a negative resistance. So, this is something, it is a very detrimental in controlling, and thus this involves a nonlinear coordinate transformations which allows to access the system nonlinearities through input channel, and thus it try to make the system linear. You have overall system nonlinear, you have a feedback nonlinear, and thus you try to cancel the nonlinearity by the feedback linearization. This is the concept. And so, then you can apply your traditional control method, or you can apply your nonlinear control also. Now, let us discuss about this figure 1, interconnecting converters with the in the multi converter power electronic systems. So, you have a source converter, it can be solar MPPT, something like that. Then you may have exchange of the power between the two buses by the bidirectional DC to DC converter, and you have a converter load 1, it may be the CPL, and and this is a resistive load, that is a constant impedance kind of loading, and other load to the source converter, and power can be bidirectional here. Let us see that how you can apply nonlinear control in this scheme. Figure 1 depicts the interconnecting converter in the multi converter power electronic system. There are two kind of load in the system: constant voltage load, or this is called a CVL. So, it will always try to take a constant load if it is trying to maintain the MPPT voltage or something like that, or or this voltage required to be fixed. And another type is the constant power load. It will always consume a constant power irrespective of the voltage with respect to some amount of range, and thus within the range current will fluctuates. The feedback linearization technique has been used to design stabilizing the robust controller. For the robust means it is insensitive to the change of state. So, that is called robust controller for PWM DC to DC converter with constant power load or the constant voltage load. Let us see that how we can employ it here. So, we just split it, we have done it in a separate way. So, we have you know that this is the input, then this is the equivalent resistance has been coupled, thereafter you have you may have a filter to wipe out these high frequencies, and thus it can be modeled as this LQ and the CQ. Thereafter, you got a constant power load and you got a resistive load, that is a constant impedance load. So, in the figure 2, the source subsystem includes, this is the equation, the state space average circuit of the DC to DC converter as well as the filter and the distributed system at the input side of the DC to DC converter. So, this is the source subsystems or the input subsystems, and this is the load subsystems. The load, the voltage and the current of the equivalent circuit of figure 2 is given by the equation 1. So, it is V n equal to R E q into I n plus L q d I dt plus V 0. Similarly, I L n equal to C E q V 0 d V 0 dt plus P y V 0 by R. This is the constant power and this is the constant voltage. So, anyway, so this will be the current in the system. So, we can write and we shall do the here feedback linearization. Using the state space averaging method during the continuous conduction mode of operation, and please mind it, all our discussion we have restricted ourselves for the continuous conduction mode, and all those equation is valid for the continuous conduction mode. Our equations and the strategies, everything will change and system will have a degradable performance in case of the discontinuous conduction mode, that we have not taken into the consideration. And it is also a type of the great research when it is a light load and all of a sudden it was discontinuous conduction mode, or the changeover between the CPLDs to the conduction mode to the discontinuous conduction mode, how the control strategy will work. That is also a great research challenge. So, anyway, so we are now debugging these aspects from our present discussion. And thus the state equation of the DC to DC converter of the figure is L d I dt equal to 1 by L V I n minus V 0. So, similarly, T V 0 dt equal to 1 by C I L minus V 0 by R minus P by V 0. And now consider a linear feedback to cancel out the nonlinearity in the system of equation 2. So, you can see that this will have a nonlinearity. So, because you can have a V 0 in denominator as well as the numerator. So, how you will tackle it? So, for this reason, the equation 2, please refer to this previous equations and the previous slide, and there is no relation between the input, that is V I n, and the nonlinearity there, and the nonlinearity, that is this CPLD, that is P by V 0. Therefore, the following change of variable is been considered, and thus we can write this one as the state. We know that always the current through the inductor and the voltage of the capacitor are the state in a linear system, but this state has to be modified to accommodate this control logics. So, it is I L minus V 0 by R minus P by V 0, this will be considered as a state and thus it is controllable. Similarly, this output voltage, error of the output voltage, that is V 0 minus V 0 ref, is considered as a x 2, this is another state, where V 0 ref or the reference voltage is the output reference voltage of the buck converter, or but any DC to DC converter you will consider here, and using the change of variables 3, the state equation 2 can be rewritten as follows. So, x 1 becomes V in by L, x 2 plus V 0 ref by L minus x 1 by R C by P x 1 by this C into x 2 plus V 0 day and x dot equal to 1 by C into x 1. So, that is the, so thus you have your state, you have chosen such a way you form a again a state space equation. So, but in a nonlinear way, and thus we can rewrite it that V L by N, assume that input voltage to be constant, then another complexity will add on. But if you take the input voltage to be constant, it is 0 anyway. So, but generally what happen, you can write it down in terms of dV n by L, that is something is unknown to you. It is k 1 into x, k 2 into, I shall define k 1 and k 2 little later, k 2 into x 2 minus that p delta, that is the deviation of the power into x 1 into C x 2 plus V 0 depth plus omega, where omega is just omega V 0 by L, and where k 1, k 2 and p perturbed are the parameter of the controller to be designed so that system becomes controllable with the nonlinear. So, what happened with the nonlinear feedback, the state equation 4 can be shown by, so this as 6. So, this equation can be rewritten in 6. So, that is your x equal to k 1 minus R C into x 1. So, this one k 1 minus 1 by L into x 2 into x 1 into this denominator C into x 2 plus V 0 R f square p minus p delta, where x dot 2 equal to 1 by C into x 1, and where p equal to p delta, then the system is linear because this part vanishes and other parameter of the controller we require to design properly. So, so that this system has an appropriate pole. So, considering the stability limit of the system. So, thus you can have a, you write a state space and you can apply, you can go to the transfer function, then apply to the eigenvalues and find it out the range of the k 1 and k 2, within that this system will work. So, this is the one of the way of designing by the feedback linearization. Now, let us come to the another interesting topic. So, that is called the sliding mode control, where we will have a chattering, we have to design the state space. Sliding mode control SMC is a robust nonlinear control system. So, there is no concept of feedback linearization, it is a hardcore nonlinear control. So, system is nonlinear and you apply nonlinear. It is not that you design the controller, you take the nonlinearity, you give the feedback, thus nonlinearity cancels out and ultimately you zero it down to the conventional linear system, but it is a totally, you accept that system is nonlinear and give a solution with a nonlinearity, and thus we generally say that it is more robust, and which is falls under the variable structure control in a short form of VSCC. So, students are required to do the nonlinear courses to understand this subject better. So, anyway, we are, if you do not have an idea of the nonlinear control, then you may find that how it will be difficult, it is quite difficult to design. For this reason, to apply in DC microgrid sliding mode control, you require to understand this sliding mode control very well. So, anyway, those assuming that you have a preliminary knowledge on the sliding mode control, we are starting the discussion. So, this variable structure system control is a bigger set. Within that, one of the set is a sliding mode control. So, SMC, depending on the switching condition a system can be considered as a set of the such systems, and such system we can subdivide one system into many subsystems, input subsystem, output subsystem, control your switching subsystem, like that. Each subsystem exhibit a fixed characteristics in a specific region of the state space. Thus, you split it. Instead of looking at the holistic the system, you split and write a different kind of state space number of state space equation for each of the subsystem. For example, in this figure 3, equivalent and the discontinuous SMC shown in the red and the blue color respectively. I am coming to this point little later. This is a DC to DC converter and this is a CPL. This will be so this red one is an equivalent SMC and it is in a constant domain, and these may be operating in a discontinuous conduction mode, and you put it to the separate system and apply a separate controller. So, what we can say here is that as shown in the figure 3, the SMC can be designed with a continuous equivalent control law as well as, for this is comma, discontinuous control law or the combination of the two. So, here it is a continuous conduction mode we assume and all those things, and CPLD may be in a discontinuous conduction mode. And this SMC sliding mode controller has a wide control applications in nonlinear system due to the robustness. So, that is something it is more stout in a change of this input signal or noise. So, it does not show any perturbation when it is subjected to a noise, and it comes back to the equilibrium point. And it is simple in implementation, mind it, it is simple in implementation if you know this subject. So, for this reason we require to study the SMC quite well, and ultimately whole challenge lies to design the sliding surface well. Anyway, I am coming to it. Consider the unified state space equation of the DC to DC converter again, and you have x dot equal to Ax plus Bu, whereas scalar x is a state of interest. It can be generally current through the inductor and the voltage across the capacitor. For example, the output voltage of the DC to DC converter. Scalar U is a control signal which is generated by using a switching control law, and A and B are the parameter matrix of the converter. So, suppose your xd is a reference value of x. So, you know it is generally its RMS value, whatever the rating. Then state tracking error can be defined as x delta. So, you want that this voltage to be this 48 volt. Thus, x delta equal to x minus xd, and accordingly you will switch it, and switching logic will be such that u switch equal to SW 1 by half 1 plus sin s. So, if there is a converter, voltage required to be high, the duty cycle required to increase. So, according this law will be followed, where S is a function of the state tracking error defined as S equal to CT transpose of the x delta, where x delta is the error, where and this vector C denotes the gradient of S with respect to the S delta. More generally, an nth order S function can be defined as x dot of t equal to ddt of lambda n minus 1. This will be a polynomial of n minus 1 into x delta, and while lambda is a positive constant defined as a candidate of the Lyapunov function and having this property that Vs equal to 1 by a square by 2. This is the energy function. So, then what we require to do? Then to ensure the controller stability and the convergence of the state trajectory into the desired point directly to the sliding surface, the switching control should guarantee the time derivative of Vs is always negative. That means energy is decreasing and it is coming to the close to the error point S equal to S not equal to 0 and S dot should be less than 0. That is a Lyapunov's energy criteria. According to the definition of S, the time derivative of S can be calculated as S dot equal to Ct of S. So, you just differentiate it. So, Ct Ax plus B u Bux. So, that is equal to Ct Ax plus half Ct Bx plus half of sin Ct Bx. This will be the x dot. So, thus S into x dot, this is the condition of the stability. We have to ensure that this has been ensured and accordingly you can design the parameter. So, this equation 12 is a necessary and sufficient condition for the stability. So, the necessary condition for the existence of the sliding mode in the vicinity of the surface x function of x and t should be 0 and can be derived as follows. Should C transpose A of x should be less than minus C transpose Bx where S is greater than 0 and Ct Ax should be greater than 0 when S is less than 0. Thus, what we can say here, see SMC in the sliding mode control system, dynamics of the state interests in the sliding mode can be rewritten as S dot equal to 0. By solving this equation, an expressions can be obtained for the initiator or the u, which is called the equivalent control law or EQ. The equivalent control law can be interpreted as a continuous control law that would remain as S dot equal to 0 if the plant dynamics are exactly known. That is one of the challenge. So, you may not know some of the parameters of your plant, and for the DC to DC converter U equivalent can be calculated by setting this equation number 11. Please refer back to the equation number 11 to be 0 and yielding this EQ equal to Ct Ax by Ct Bx. So, and thus please go back to the equation number 13. So, this is the equation number 13. So, this is a necessary and sufficient condition also. To ensure that 13 is satisfied, EQ needs to satisfy the following equalities. So, this is the equalities. EQ should be greater than 0 equal to Ct Ax by Ct Bx equal to is less than equal to 1. Thus, SMC is an important control approach, an important robust control approach in the nonlinear system. There are so many methods and I have chosen one of the very typical and very interesting control technique. So, DC microgrid also you can apply lot of control technique or you can analyze the system or you can enhance the stability by designing a proper control logics. And more important issue in designing the SMC is to design the switching law or the sliding, we generally in terms of the we generally say it is a sliding surface. The switching control law to derive the plant state to a switching surface and maintain it to the surface upon interpretation or inception. So, this is the one of the application of the nonlinear control in DC microgrid. We have so many technique to be applied and studied, so that it's we can push more on the control logic and take care of the large scale variations, and due to the time constant we cannot discuss all the topic. Thank you so much for your attention. Students are requested to, while doing these courses, has to be very thorough with the different control technique as well as the sliding mode control, then only they can understand or appreciate this course better. And next class is our last class, and that will be our conclusions. There we try to speak about ultimately what we have discussed, that we will try to summarize there, and also we will see, we will show you the scopes as a practitioner engineers, as a researcher and different stakeholder, what is why you should study the microgrid. That is something we try to justify in our next class as a conclusion class. Thank you so much indeed.